and heren, ladies and gentlemen. Hello. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open the session and I welcome you all to the public defense of Nicolas Moens. Nicolas Moens has presented to the faculty his PhD thesis on the topic radiation hydrodynamics of massive star outflows, in partial fulfillment of the requirements for obtaining the degree of PhD in sciences, physics. He shall now publicly defend his PhD thesis. Before he does that, let me introduce you the members of the examination committee. I have to start with excusing a few of our colleagues because of all our formal duties, but be assured they all were present at the preliminary defense, which took place successfully, which is why we are here. So one of the persons that is absent is my direct colleague, Tom van Doorselare. He works at the Center for Plasma Astrophysics at the Department of Mathematics. Another colleague that is excused is Professor Leen Dessin from the Institute of Astronomy, KU Leuven. Another excuse has been received from Dr. Andreas Sander from Heidelberg University. And then I can come to the members that are actually here in one form or another. One, Dr. Dylan Key is online. So Dylan, welcome.
Hello.
He is from the National Solar Observatory, USA. Then I introduce here the promoters from this thesis. So that is Dr. Iliak Elmela, who works at the Astrophysics Institute of Grenoble, but will move very soon to be assistant professor at the University of Santiago de Chile. And then the promoter of this work, also John Zundquist from the Institute of Astronomy, KU Leuven. With that, I give the floor to you, Nicolas. You are invited to give a presentation of about 45 minutes about your work, and then we will question and discuss your work. Thank you.
All right. Thank you, Annie. Also, thanks. I'll give you a second here. Also, thank you for everyone who's here. It's truly amazing to see all my colleagues, my friends, family. It's really nice to see you. Are you? Yeah. All right. So, radiation hydrodynamics of massive star outflows. I'm going to start my presentation by showing you this picture that the James Webb Space Telescope team released last month, just in time for my public PhD defense. Super nice. And what you see in this picture is the nebula surrounding a Wolf-Rayet star. So the Wolf-Rayet star is here in the middle. You can't really see it. It's a very small dot. It's smaller than a pixel, what you can see on screen, but it's there. And surrounding this Wolf-Rayet star is this nice pinkish cloud, and this is a nebula. And this nebula is gas that's being blown away by this central object and is creating this nice shape in space. So the Wolf-Rayet star in the middle is not like our sun. It's a lot more massive. It's about 20 times as heavy as our sun. It has a radius that's about 10 times larger than our sun. It's a lot hotter than our sun, 50,000 Kelvin as an effective temperature instead of the sun's 7,000. And it's 500,000 times as luminous. And this star, as you can see from the nebula you see, loses a lot of mass. And it loses so much mass that in every 10,000 years, it loses about the mass of the sun. Now, 10,000 years sound like a long time, but on an astronomical scale, that's not that much. So this is a really lot of gas that this star is pushing outward in the stellar wind. So this gas has been blown away, that goes back to the universe to be recycled and to form new stars. And so what we see here is another picture, a picture of the Orion Nebula surrounding the constellation Orion. And if you know a bit of the night sky, you can see here Orion's belt, and here then the bottom and top stars that you easily recognize if you look at night sky. And what this Orion Nebula is, this is a region where stars are being formed. So here in this gas cloud, parts of the gas cloud collapse. They attract each other gravitationally to form new stars. And what you can see on this picture is that not all stars are the same. There are some stars that are a bit brighter, some stars that are a bit less bright, stars that have more of a bluish hue and more of a reddish hue. And granted that in this picture, a lot of that is due to the gas that's interfering and in front or behind stars. But that's also just a fact about stars. Not all stars are the same. And so if we as astronomers want to look at all different of stars that we can see, we try to categorize them and put them on a diagram. And we can do that in the following way, where we plot all the stars in a square, where we plot the bluish stars, which correspond to having a high temperature on the left-hand side of the diagram. We plot the reddish star, which corresponds to a less hot, but still less hot temperature on the right side. And top to bottom, we go very bright stars and very low brightness stars, or dim stars. Yeah. And if we plot all the stars that we can see on such a diagram, we call this a Hertzsprung-Russell diagram, we see that some patterns emerge. And the most striking feature on this diagram maybe is this large bunch of stars on this diagonal line. And this is what we call the main sequence. Yeah, and then next to the main sequence, we also find some blobs of stars here on top, to the top right, which are cooler and brighter. And also there's the white dwarfs on top. So over the past many years, we've come to understand why stars sort of agglomerate in this shape on the diagram. And that is basically because this is a direct effect of the evolution of these stars. So here on the right, I plot basically the same diagram. It's again a Hertzsprung-Russell diagram, but now with some, I don't plot the stars, but I draw some lines. And again, here we have the main sequence. And it appears that the main sequence is on the Hertzsprung-Russell diagram where stars are born. Yeah? So when the clouds collapse, the star forms and starts fusing hydrogen. They lie here on the main sequence. And stars that have high masses go to the top left side, or are born on the top left side of this main sequence, and stars that have low masses go on the bottom right side. And then what happens when the stars evolve and they age, they move away from this main sequence, and what you see here in different colors, orange, green, blue, and pink, are the evolutionary tracks of these stars. So these stars start as main sequence stars, and then low mass stars become subgiants and then red giants. And then, for me more interesting, the massive stars. We have a nice example here of a 15 solar mass star that becomes a blue supergiant, a yellow supergiant, and a red supergiant. And even more interesting for my work is here this 60 solar mass star that starts out as a main sequence star, becomes a blue supergiant, a luminous blue variable, and then the Wolf-Rayet phase, the Wolf-Rayet star. So as you can see, the WR, the Wolf-Rayet phase, is the last point in this star's evolution. So after this point, the star stops evolving and it explodes in a supernova. Yeah? So let me repeat this picture that I just painted in a more graphical manner. Stars are born in star formation clouds, like the Orion Nebula. For massive stars, they become then these blue main sequence stars, O stars. They go through a bunch of evolutionary phases, such as luminous blue variable phase, and also be a blue supergiant phase. And then if the star is massive enough, it will go to a Wolf-Rayet phase. Yeah? To become a Wolf-Rayet phase, the star has to get rid of its outer layers in some way or another. This can be binary interaction, or this can be the star itself shedding its layer with radiation pressure. But what we're left with is a Wolf-Rayet star. And this Wolf-Rayet star forms these nebulas. This has very high density winds, so throwing out material back into the stellar medium to form new star formation regions. And after the Wolf-Rayet phase is done, the star collapses, explodes, and becomes either a black hole, it goes to the supernova, becomes either a black hole or a neutron star. So because these Wolf-Rayet stars are the final piece in the evolutionary puzzle, and because they have such significant mass loss and so much material that they throw out, it's very important for us to understand how Wolf-Rayet stars work if you want to understand the black hole graveyard, so the distribution of black holes that we can find with the LIGO detectors, for example, and if we want to understand how material is being recycled in the universe, and thus the chemical and dynamical feedback from stars to the local universe. Okay. So if you want to observe something, if you want to learn something from stars as astronomers, we typically look at the objects with our telescopes, but instead of taking pretty pictures, what we typically try to get are spectra. And I've a picture of a couple of spectra from Wolf-Rayet stars here. What we do to get a spectra is we look at the different wavelengths of light that the star emits, and then per wavelength, we see how much light So per color of light or per wavelength of light, we see how much light reaches the telescope. And different elements of the periodic table, they all leave their effects or they leave their influence on this spectra, and they leave their signatures. And by analyzing these signatures and these spectra, we can sort of work back what the star is made up of, so what the composition of the star is. We can learn what the temperature of the star is, the mass loss rate, and that kind of stuff. So the spectra for us are very important. However, the spectra will also be affected by the wind that is in between our telescopes and the star. So if you have a star that's emitting light, but in between the star and the telescope is this very dense wind of the Wolf-Rayet star, our spectra will be affected and affected by the wind. Okay. So if we want to be able to interpret our observations from stars, it's very important that we also understand the stellar winds, how they form, what their shape are, or what the structure of these winds is. So next good question, what is a stellar wind? So stars typically are held together by gravity, but in most stars, also in our sun, there can be forces that actually push away parts of the outer envelope of the star. So in our sun, this happens because there is a big pressure gradient between the sun itself and then outer space. And so this causes a driving force, a force that pushes gas away. And if this force is bigger than gravity or greater than gravity, your material will be able to accelerate outwards. In stellar wind theory, we often use this symbol gamma, the Eddington parameter, and it's the driving force over gravity. So if gamma is greater than 1, you can drive a wind. So like I said, in the sun, this is driven by gas pressure, but for massive stars, this is typically driven by radiation. So massive stars are a lot more luminous, so they have a lot of light that they put out. And people that have done a bit of physics know that photons also have momentum, albeit very little. So the momentum of a photon goes as the Planck constant, which is like a natural constant that has a very small value. So photons have little of momentum. And by the interaction between the photons and the gas particles, so the photons being absorbed by a gas particle or scattered by these gas particles, they can transfer their momentum from the light to the gas, thereby driving the particles of the wind upwards. And an important quantity here in this whole story of interaction is the opacity, which we typically denote by the Greek letter kappa. And this opacity basically says how likely your gas is to absorb or scatter with light. Yeah? So a good way to think about opacity in an everyday life kind of way. Things with a low opacity are glass and air. We can easily see through glass and air. They're not opaque. And in stellar wind theory, a good example of a low opacity region are the winds around O stars, important for later. And on the other hand, high opacity is something that we know from looking at concrete. You can't see through concrete. Fog is a bit opaque. You can't easily see through fog. Your light gets absorbed or scatters on fog. And a good example of what an optically thick or a high opacity regime is in stellar winds, we have to look at the winds of Wolf-Rayet stars. Yeah? So O stars optically thin, Wolf-Rayet stars optically thick. So for O stars, we have a good theory of how the winds are driven, these optically thin winds. And it's a bit of a complex process, but I'm going to try and explain it here as clearly as possible. So O stars are driven due to the interaction between the light from the star and a very specific wavelength of light in an atomic transition. So atoms are very efficient at absorbing photons of one specific wavelength. And I've plotted that here. So here you have our star shining in different wavelengths, what I've indicated here by different colors. And here we have what an atom can absorb. And you see here that the absorption pattern for this particular atom is centered around this dotted line, and it's not absorbing the other three wavelengths. Yeah? So what happens in this O star wind, this particle will absorb this specific wavelength of light. It will be accelerated ever slightly. it will move out a bit further in the wind. It will gain a bit of velocity, and due to that velocity, it will gain a Doppler shift, which, oh, that's the wrong direction. It will gain a Doppler shift, which makes it possible for that same atom to also absorb light from other wavelengths. It will again gain momentum. This process repeats. It will Doppler shift more, it will Doppler shift more. And in that way, the very fine absorption lines of these atoms are very efficient at picking up loads of radiation coming from your O-star. Now, one complicated thing in O-stars, these stars have some metal abundances. So there's iron and other higher elements in these stars. And these elements are known for having lots and lots and lots of these transitions. So what I've drawn here is one dip. That's a bit of an idealization. In real life, these atoms have, at different wavelengths, very many dips. And a nice picture of this here is what we call the Grothian diagram of, I think, titanium. And what we see here is all the different energy transitions that exist in the titanium molecule. Not all of these will contribute to the line driving of O-stars, but many of these will. And I think that we typically say around 40,000 lines are important in UV, in O-star driven winds. Luckily, we don't have to care about like all these millions of lines. What we can do is we can find a nice analytic formula for that nicely fits this entire process of the line being Doppler shifted and then takes into account all these lines. And that comes in the form of the CAK force, or the CAK formulation for line force. And what we see here is quite a complicated formula, but it also encompasses a complicated process. And what it gets is basically this opacity, this kappa, as a function of the density of the wind, rho, and your velocity gradient. Because if you have a higher velocity gradient, you accelerate harder, and you have more of this Doppler shifting. That's how you can interpret it. What's also in this formula are the constants alpha and q bar, and they basically entail how your millions of lines are distributed along wavelength and force, or quality or strength of the line. So I said that O-stars have a optically thin wind. The winds of O-stars are not very opaque, except for in this line, of course. And that's necessary because this line driving can only work if your line absorbs in this center and there's no opacity to the left and to the right of that line. So what do O-stars look like? This is an idealized case. We have an O-star, which is a ball, and the photosphere of the O-star, which is basically the surface that we see of the star, is just on top of the ball, and behind the photostar, your wind takes off here. The wind is optically thin, the star itself is optically thick. Okay, this is in stark contrast with how Wolf-Rayet stars look. This is my beautiful drawing of a Wolf-Rayet star, where you see the actual star that I've indicated here with this dark blue blob, and this dark blue blob is encompassed in this very optically thick wind, this lighter blue blob. And this wind is so thick that actually when we try to see the star, it's impossible for us to see the star. We will always see the wind that's around this star. Basically like how if we look through fog, we can't see the other side of the fog, but our vision stops somewhere in the fog, right? And from observations, we know that this optically thick wind is dynamically very active. It's not just an outflowing material. There's a lot of like convective motions going on in a very dynamic system. For O-stars, we know that the winds are driven by this line driving, by the CAK theory. But for optically thick radiation-driven winds, the winds from Wolf-Rayet stars, we actually don't have an idea yet, up until recently. So that's part of where this thesis is about, finding the mechanism behind these winds. Okay. So we know that line driving cannot work on the inside of this photosphere, this red dotted line. Here is the wind optically thin, here is the wind optically thick, more or less. So we have to find a launching mechanism for this first part of the wind from the actual core of the star to the photosphere, to the optically thin regions. And a hint comes from looking at the temperature of where we find this photosphere typically. From observations, we can infer that the photosphere of these stars is typically around 50,000 to 100,000 Kelvin. Important number, because if we look at the opacity, the integrated opacity of stellar gas, we see that slightly hotter than 100,000 Kelvin, we have to look at the green curve here, there's typically a high bump in the available opacity in the stellar gas. So if your gas, so this opacity depends a lot on how the ionization balance in your gas is. So if your gas is hot enough, your gas becomes suddenly opaque or more opaque. Okay. And the reason that it's at this temperature is because there's certain ions, especially I think iron 4, that recombines at these temperatures. So that's true for all Wolf-Rayet stars. So this opacity bump, this iron opacity bump, what we saw in the previous figure, can be maybe used to drive the wind of the Wolf-Rayet star. So we can do that. We can do a simple gravity versus driving force analysis, where we have here, you can imagine the star is here. This is a line that goes away from the star. Here we have our photosphere. So we know that this iron opacity bump that I showed you earlier is a bit hotter than the photosphere. So it has to be in between the star and the photosphere. And if we then look at whether or not gas particles are accelerated, if the driving force is stronger or weaker than gravity, we can calculate that, and we can see that in the beginning, where the iron opacity bump is very effective, we can have some driving. Our wind is able to pick up some velocity, this black curve is velocity. But then after a certain point, you're outside of this hot iron opacity bump region. There's suddenly less opacity available, so your photons don't push the gas as much anymore, and your wind starts decelerating until you're after the photosphere. So this can't be the full picture of how Wolf-Rayet stars work, because as you can see from this beautiful drawing, at a certain point, your wind has no velocity, means that it's falling back onto the star. It has not produced a full wind. However, we are now, with our gas, outside of this photosphere. So we're in the domain where the wind is more or less optically thin, or more optically thin. And this is the regime where this line driving that also works in O-stars can take over. So for Wolf-Rayet winds, we can maybe think, okay, can be a combination of first this iron opacity bump that drives the wind up until the photosphere, and then this line driving that takes over in the outer wind. We call this the hybrid opacity mechanism, and this was worked a lot on by Luca, who's in this room there. And it seems to work. However, when we worked a lot on this theory, we didn't really quite know all the line force parameters that are necessary for Wolf-Rayet winds. So accidentally, by chance, we basically increased the line force a bit, which makes, if we correct for that, makes the hybrid opacity mechanism just fail barely. So the hypothesis is, since we also know that these optically thick winds are very dynamically stable, maybe it's a 3D effect, an instability, or the moving of gas in the lateral plane that makes the wind more efficient and makes us able to launch the wind. So that's what we plan on doing. We try, instead of doing this 1D simple force analysis, we try to fully model the wind in a 3D radiation hydrodynamic setup. So what does this mean, radiation hydrodynamics? That means first that we want to model hydrodynamics. And hydrodynamics is a study of how gases flow. And we do that by solving these three scary equations. I'm gonna go through them, so no worries. So what these equations are, these are the continuity equation, the momentum equation, and the gas energy equation. And they describe gas energy, momentum, and gas density. So what this equation basically says is, if you have a given distribution of gas, and you know, so that's rho, the gas density at every point in the room, you know your velocity v, then you can predict, or you can model with this equation how the densities will change over time. And the same here for the momentum equation. If you have at a certain point a momentum in your, or a given flow field in your room, and you know the pressure, then you can evolve and model how your velocity field in the room will change. And the same is true for the gas energy density, which correlates basically, to understand it easy, with temperature of the gas, or the amount of energy that's within the gas. So this is hydrodynamics, but we want to do radiation hydrodynamics because we're also interested in the radiation field, which pushes the gas in and out. And for that, we add a description of the radiation field. And there's many ways of doing it. And the way that we do it in our work, or the way that I did, was by solving what we call zeroth order moments, zeroth moment of the radiative transfer equation or the radiation energy density equation. Okay, and this basically models if you have a given distribution of radiation energy in a room, and you know how the radiation will flow with it, how the radiation shines, basically the flux of the radiation. Then you can model how this radiation will behave towards the future. Okay, all these equations basically have the same shape. You have this weird curly thing with a letter T underneath it. Then you have the density or the quantity that describes. Then you have this triangle thingy, and then the same density with the velocity. And what this is we call these the equations in their conservative form. And what that means basically is the equation describes the conservation of density or the conservation of mass. What does this curly thing and this triangle thingy mean? The curly thingy, we call this a derivative, partial derivative, basically says at any point in space how much your density will change with respect to time. Yeah? The triangle thingy, we call this the divergence or the Nabla operator, says basically if you have a point in space and you have gas flowing in and you have gas flowing out, what the net inflow minus the net flow is, or the net adding the net, what you add net to that point. So what this equation basically means is if you have a point of space, the amount of density that will, or the amount of density that will change in the space is equal to the amount of density that you let flow in, that you make flow in that piece of field, right? And this is, I've explained it here for the density equation, but the same also for the momentum and the energy equations. So we have now our equations for gas dynamics. We have our equations for radiation. We're also interested in the interaction between the two. So one of the possible ways that this can interact is with this radiation force that I explained earlier. Yeah? And this radiation force, so that adds momentum to your gas. So this the second equation, the momentum equation, you can see this basically as Newton's second law, where you say that the change in velocity or your acceleration is equal to the forces that act upon it. F equals ma. And we see here again in this radiation force, we have the opacity kappa for this interaction, and F is the amount of light that flows through. Yeah. So higher flux, higher force, higher opacity, higher force. This radiation force, if you add that to your system, you also have to add that to your energy, your kinetic energy that's being added, and the work that the radiation provides to conserve your total energy. Another important effect is the heating and the cooling. And you all know this from sitting on a terrace in a bar in winter when you have these heat lamps shining on you. This is basically the radiation that's being absorbed by your body, giving you energy and heating up. So the heating and cooling, this Q dot, that's basically the energy interaction between the radiation fields and the gas energy density fields. And then finally, we have gravity to have our force balance. The radiation pushes your gas outwards, and the gravity pushes your gas inwards. Then one more thing that we need is we need to know what our radiation flux will be like. And for this, we use what we call the flux-limited diffusion approximation. And this is an analytical approximation for solving your radiation equations. And what this approximation basically says is that if you're in a very optically thick regime, your radiation will behave as if it's a diffusive process. So you all know this diffusive process for if you have, like, you've seen that on YouTube probably, if you have a glass of water and you put some ink in it, this ink will slowly diffuse outwards and become equal over the entire glass. And that's basically how we describe the radiation in our optically thick parts of the wind. And we do it this way because it's computationally cheaper than solving what we call the full radiative transfer equation. And gives us a nice way of, on a computationally feasible manner, solving all these equations at the same time for a prolonged number of time. Okay. So part of my work was to implement these equations in MP AMR Vec 3.0 right now, not 2.2 anymore. I have to adapt that. Okay. So we have our equations now. We know what we want to do. We want to model these Wolf-Rayet outflows. So we can do that. And to do that, we take this numerical grids. So we say, okay, this is the space that we're interested in. We imagine these grids right next to the Wolf-Rayet core. So this is the Wolf-Rayet core. And then in these grids, we have thousands of cells. And in each of these cells, we consider the density, the momentum, the energy and radiation energy. And then we use our 4 equations that we saw earlier to evolve these fields and to predict how the gas flow will behave. So to do that, we need to do a few more things. At the bottom of our grid, we need to, so we call this the bottom of the grid, because here is the star and this is the outflow. Right? So at the bottom of our grid, which is on the left here, we have to set what density the stellar core is at. We have to set how much flux is flowing in. These are the stellar parameters. And then we have to provide some initial conditions, because we have to evolve the model from initial conditions. And then we solve upon that grid the equations that I showed earlier, together with this hybrid opacity description for the opacity. So I'm going to show you now a movie of how we solve these equations, or what the result of solving this equation is. And what you're going to see is, so this is basically the same numerical box, but we stretched a bit to make it look a bit more like a star. The stellar core is here, and this is stellar wind. Here we have the density distribution, the radial velocity distribution, the lateral velocity, so the sideways velocity is radial. Okay, I'm going to play you the movie, and this is so the results that we have from our calculations. Yeah. So what you can see immediately is that this is far from a simple symmetric 1D system. Yeah, there's a lot of motion going on. It's a very complex process. So yeah, it's very complex, and these calculations are necessary to sort of see what type of motions are going on here. The full movie that plays here in about 5 seconds, in real life around the start takes 5 hours. Okay, and so yeah, this radius here is about 1 times the radius of our sun, and so this is quite a big domain. So yeah, we have this. And so, like I said, important that we have these very complex structures. Hard to understand, but good news. Overall, we see that the color here is yellow in this radial velocity plot, meaning that we have an actual outflow, meaning that we can produce an actual stellar wind. And so these are the first ever multi-D Wolf-Rayet wind models, and they're immediately able to explain basically the winds of Wolf-Rayet stars without this extra force that we needed with the line force parameters. Okay, so now we maybe want to understand why this suddenly works in 2D or in multi-D and not in 1D. And for that, we can look at the same simulation, but now frame by frame. And what we can see here is, so this is the density plot. The star is now at the bottom, and all these frames next to one another are at the beginning of the simulation, and then each time about 10 minutes later in real life. And the takeaway, or what you should take away from this figure, is that here at the bottom of the simulation is where the complex stuff starts to happen, right? So this is all looking smooth, 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 and then here we have some complex stuff happening, and this is caused by a convective radiative instability because of this iron opacity bump, and then this complex stuff is being blown out into the wind, and that's where all this complexity comes from. Yeah. So where is this complex stuff happening? This complex stuff is happening in the regions of the wind that are dominated by this iron opacity bump. And so the outer wind is, like I said earlier, driven by this line drive. But in this line-driven wind, we have some of these blue clumps. And the blue clumps, these blue blobs, means basically that there's a lot of material there. If there's a lot of material there, that means that that part of the wind is suddenly not optically thick anymore. So we can start wondering how it comes that these parts of the wind are still blown outwards. And we can think about that by zooming in on these blobs. And what I plot here is this gamma factor from earlier, where we have the radiation force over the gravity force. And what you see then is that if the material is gray, we actually expect the material to be accelerated inwards back to the star. Star is at the bottom of the spot. And when the material is red, we expect the gas to be flowing outwards, or accelerated outwards at least. So the blob is gray. Still, if we look at our simulation, we see most of the blobs flowing outwards. So how is this possible? We can look at our momentum equation, where we have the radiation and the gravity. And so these guys don't do it because these give negative results. So your momentum has to go positive or has to go up. So what's happening here is hidden in this advection term. It's basically the inflow of momentum in your clump. Or we can understand that more clearly as ram pressure. We have this lightweight or light density red material that's being accelerated really hard, and that crashes into the thicker clump, blowing the clump outwards. So this makes this whole wind process quite complex. To explain this, we have our multi-D wind launching mechanism, and what happens is we need structure formation at the bottom of our winds in the iron opacity bump. Then that material has to vacate stuff so that the low density material can be quickly accelerated via this line driving mechanism that we also have in Ostar winds. And then we have this fast low density gas that's accelerated highly via line driving that crashes into these high density clumps, and that way accelerate the clumps and the growth of your winds, or most of your winds. Okay. So we can also do this in 3D. I'm gonna show you here the movement of the clumps in the same simulation, but now in 3D, where we have the star here at the bottom. So this is the outflow direction. And what we plot here with these yellow blobs, what I will show you later, is the clumps that are 5 times heavier than average surroundings. So in the beginning, we have some initial conditions that flow away, but then you see all these clumps being pushed outwards by this lightweight material. Okay. So that's also just to show that we can also we can produce these models not only in 2D, but also in 3D. And if we have these 3D models, so I plot here density and the velocity, but we also have the temperature structure, and thus also how we can know from these models how radiation will react with your gas, because we know the temperature, and then density and the opacities. And that's basically everything that we want to know about Wolf-Rayet winds, right? We know how the wind is structured, we understand the mass loss, and now by knowing this complete gas structure, we can also use these structures to compute how radiation will transfer through this wind to synthesize spectra. So that means to compute theoretical spectra that we would get from this Wolf-Rayet winds. So what we can do is we can take this cube wind simulation, we can sort of extrapolate it around star, and then we can perform a different type of calculations on it to sort of predict what type of things that we would see, right? And that's a nice, because we have these 3D simulations through time, we can also simulate what we would see through time. And so this is what the Wolf-Rayet star would look like to you if you would be there through time. So what we have here in the black circle is the actual stellar core, and what we see in the dotted circle, which is maybe a bit hard visible, is the photosphere. So that's the actual light that we see. So the core is hidden within this photosphere, and we do that. We have that here at the continuum wavelength and at the wavelength for a given line, which is important because if you want to learn something about stars, we look at these spectral lines, like I told you earlier, and we can, by integrating this over the full surface, we can generate these spectral lines and predict what spectral lines of such a star would look like. Interesting here is that these spectral lines change through time, and we call this a line profile variability, and that's also something that we actually see from real Wolf-Rayet stars. And here on the left, we see how the average brightness of the stars will vary, deriving from temperature flux. So, and this is also something that astronomers use often. It's called photometry, where they look at how stars flicker, basically to learn about the structure within the star. So if we go back to our nice picture from the beginning, if you were able to zoom in all the way to the center, zoom in very much because this picture is light years across, and you would look at the star, first of all, you would go blind, but then right before that, this is what you would see. Okay. All right. So that was one model for one set of stellar parameters. What we also can do now is look at the effect of different stellar parameters on the, like what the effect of different stellar parameters is on the structure and the typical characteristics of this wind. Yeah? So one way to sort of characterize this wind is this diagram here, where we plot the x-axis is the distance away from the star, the y-axis is the radial velocity, and then this color plot is how often you see gas at that distance at that given radial velocity. So you see here, close to the star, most of the material has zero velocity, so close to the star on the left, zero velocity here. And then if you get farther away, so more to the right of the plot, you see that your velocity goes up. And that's what your wind is basically. If you're farther away, you go faster and faster. But we also see that it's not a simple line, because we have all this structure, material going up and down, slower and faster. We have a certain distribution of velocities. And if we now do this so this is for the model that I just showed you, if we do this now for different inputs of stellar parameters, we can compare these models like I do here, where here, this is the first model that we saw. If we lower and lower the luminosity input at the bottom of the star, we get different structures of the wind. So here we have this nice wind that departs and gets accelerated and just leaves the system. And this is what we expect for a high luminosity Wolf-Rayet star. But if you lower the luminosity a bit, if you lower the Eddington ratio, so this driving over gravity term, then we see that your wind has a harder time with really escaping, and there's a lot of material that has a velocity below zero. So that's actually negative velocity, so that's material that's falling back on the star. So this corresponds to a wind where a lot of material is going up and down again, and this is very violent dynamic atmosphere. And then if we lower the luminosity even more, we get a wind like this. And this is very curious. Basically, first for a very long time, you don't really have a wind. You have material flowing up and down, but there's no real net outflow. And then at a certain point, there is an outflow. At a certain point, your wind accelerates, and you get an outflow. If we simplify this picture a bit and we look at the actual average velocities of these simulations, so this purple one was the one most on the right, this orange one is the most on the left, and we see that the average velocity profiles for this purple one is actually quite stagnant for a while before it accelerates. And if we look then at the photospheric radii, which I've plotted here with this full dots, then we see that most of the winds start and then have their photospheric radii somewhere far in the wind. And then that this orange line first has its photospheric radius, and then the wind starts. And if you remember, this is actually quite reminiscent of what we saw or what we expect an Ostar wind to look like, right? For these parameters here, because it's Wolf-Rayet masses and Wolf-Rayet radii, this is not a main sequent Ostar, which are much bigger, but this is something that we call a hot subdwarf or an O subdwarf. If we compare the mass loss rate, so the net outflow of material from these models, we can see also a sudden change in behavior. So for the high luminous Wolf-Rayet star and the dynamical Wolf-Rayet stars, we're sort of on this line. And then for this hot O, this O subdwarf model, we suddenly make this angle and we go down. And this mass loss rate is something that's very important in stellar structure calculations. Yeah, so like I said, this O star is basically very similar to what we so this O subdwarf is very similar to what we expect an O star to look like. Yeah. So that basically invited us to also try to run an O star. And that's what you can see here. So this is the same simulation, but now for typical O star parameters. And what's very interesting here is that we first of all reproduce this behavior. So you get this stagnant, turbulent wind with on top of that, this line-driven high velocity winds. So this is the part that we already understand quite well. That's the CAK wind, this line driving wind. And this part is basically what's inside the star. And this is very interesting because we think that this might be the subsurface convection zone. And subsurface convection zones, maybe doesn't, I didn't really introduce this, but this is very interesting effect that has very many promising, exciting future work built upon. So this subsurface convection is, for example, important for stellar structure, might be important in Ostar asteroseismology, line formation, so spectral synthesis and macroturbulence. So that's basically it. Let me conclude quickly with what we've done. So we've developed tools with which we can compute 3D radiation hydrodynamic models of stars. We've used these tools to create the first 3D model of a Wolf-Rayet wind, thereby uncovering what the launching mechanism of these winds actually are. We've also seen that O subdwarfs and Wolf-Rayet winds are actually quite related and just separated by how much luminosity the star has. And very promising for the future, we might be able to model subsurface convection zone. So what I want to say that basically my PhD is done, but there's a lot of interesting stuff that's going to build off these models. Thank you.
Yes. Thank you very much, Nicolas, for this enlightening presentation. So now is the time for us to ask some more questions. I will first give the floor to the jury member that is the furthest away, both literally and, also on the screen. So, Key, please go ahead, and I hope everything is set up so that it works right away. Thank you.
Okay, great. Am I coming through all right?
Yes, we hear you.
Great. Okay. Well, first off, yeah, very nice work. Congratulations. This is, of course, as you know, I think very important and interesting work that you've been doing here. What I want to start out with is actually your last point there. Namely that there is a lot of future work to be done here, and a lot of interesting things that can be built off of your thesis. Particularly, you somewhat, I think you somewhat undersold the complexity of what you've actually already done here in developing a 3D radiation hydrodynamics simulation framework, and the fact that there are, of course, then some approximations that need to be taken to develop such a code. So in launching these sorts of future projects, I'm interested in what you think the approximation that needs to be relaxed first is to make that future progress.
So one thing that's, so I think when you talk about approximations, you mainly talk about this flux limited diffusion that we work with. Which I have, I'll pull up the slide again. Yeah. So basically, well, so this equation is completely correct, but it's hard for us to compute what this flux F is. So to compute this flux F, we basically use this simpler way to sort of approximate it, right? And so this is, for now, this is a good model because if you want to do dynamics, there's not much wrong with flux limited diffusion. It's very well at recreating dynamics, especially in this one. One thing that we could do though is what we call anisotropic flux limited diffusion, and I think we've discussed it before, and that is where, so this flux limited diffusion, it says, okay, my flux goes as the gradient of my radiation energy density, and depends on this opacity kappa. In this line driving mechanism, your opacity kappa depends on the direction in which the gas is flowing. So the opacity along velocity gradient is higher than the opacity perpendicular to velocity gradient. And right now in our models, we really don't take that into account. And I think that can actually be very interesting to see what the effect of this anisotropic diffusion is on the formation of these structures in the lateral plane in our simulations. So I think, and if we talk about approximations that we can easily resolve, I think that this is one of the first things that we should tackle. That being said, it's also semi-developed. The models have to just be put out there.
Mm-hmm. Great. I definitely agree that anisotropic diffusion will be an important step forward. Related to that, actually, you've commented a little bit about formation of structure in the lateral plane from that anisotropic diffusion. I'm wondering about also then the structure formation in the radial direction as well from that. Do you think that that'll have much of an effect on, for instance, clumping factors that you're seeing, or?
I mean, yeah, it's definitely possible, right? Because if your clumps become bigger laterally, they will also definitely behave different in the radial direction. I think, yeah, that's sure. I think, yeah. It's overall an important difference. Yeah.
Mm-hmm. Shall I keep going, or are we gonna pass and
ask another question, though?
All right, great. Okay. Wonderful. Okay. I suppose also in line with this future work and future development, I know that some of your successors are in the audience who will be using this code and moving forward with it. So I guess I wonder what your advice to them would be in utilizing and deploying this code in their own work.
Oh, it's a bit of a vague question. No?
So sure, yes. Sorry.
Okay. Advice. It's complex modeling, right? There's a lot of fine tuning of a lot of parameters, and what I never really did, or what I should have done better, maybe, is to keep track of what the differences are between actual physical effects or the effects of actual physical parameters and the effects of the limitations of our numerical solvers, right? So I think besides developing these models for O-stars and developing the models for other type of stars, such as my new colleagues or my old colleagues are doing, I think it's also a good time to maybe start looking at doing some resolution studies. What is the effect of the what we call the pseudoplanar correction, that kind of stuff? Because, yeah, we sort of glanced over it a bit, maybe.
Sure.
I'm not sure if giving more work is good advice, but sorry.
No, but that's definitely the sorts of things that I was. I appreciate it was a vague question, but that's the sort of things that I was hoping to get at there. So,
yep.
Good. No, I think I mean those are the main things that were rattling around in my head. So I'm fine to pass on then back to the rest of the jury and again say congratulations on some nice work.
Thank you, Bill.
Okay, thank you, Dr. Key. So we will move on with some questions. First, I did receive some questions from some of the absent jury members, so I'll probably ask those first. Got some questions from my colleague, Tom van Doorselaar, who, not unsurprisingly, obviously asks the question about magnetic fields, which are missing from your work as yet. Let's put it this way. So there was already some discussion about that in the pre-defense, and so here are his thoughts. What would be the influence of magnetic fields on the clumping? What would be the effect of added magnetic pressures, the Lorentz force that comes in? Can you maybe speculate at this moment on that?
Yeah. So I think we've also done another old colleague, Florian is not old, a colleague of ours, previous colleague, worked on magnetic fields in Ostar winds, and basically looked at how the LDI instability, so this instability in Ostar winds, is affected by magnetic fields. And what he finds there is basically that, if I remember correctly, that the magnetic fields basically prevent structures from breaking up. I remember correctly? Yeah. So I'm not sure if that's fully applicable as well in our optically thick winds. I'm also not sure actually what type of magnetic fields formations we expect Wolf-Rayet stars to have, because they're very evolved.
Would that be a problem in your simulations, and especially the fact that you explain the fact that are still going out by ram pressure effects on these clumps? But if they don't break up, then that might actually counteract.
Yeah.
Is that something that you can discuss, or?
Yeah, it's a very good point. So yeah, then we're talking about small scale magnetic fields and not some global magnetic field that's given by the stellar dynamo or something. Yeah, that's a very good question. Not sure. I think we can honestly to incorporate magnetic fields in our simulations that would require a lot of work, because we do some with this weird geometry that we.
Okay. Okay. I'll move on to the next question then, which is a bit more concrete here, in the sense that you presented also the comparison between your simulation and this Poniatowski et al. I don't know whether you can put up the slide somewhere, but you made a very precise comparison there. And one of the points that you said is that there is still a difference on the order of about few to 10%, depending on the location where you look. My colleague's comment is the following. Of course, that directly translates also in the corresponding mass loss rate. Yeah. And so
I'm not really following what comparison we're talking about. Is it in the T's or?
The mass flow rate would be
rate.
on the order of 10% difference from the Poniatowski.
Okay.
Right? Mm-hmm. And so then the question is really, if there really is a 10% difference, does that directly impact things that you also mentioned in your introduction, basically, the fact that these mass flow rates actually determine evolutionary paths? So is a 10% difference sufficient to show up in evolutionary paths? That's, I guess, the question.
I think definitely, yes. We've had another colleague of ours, not old, who worked on not for Wolf-Rayet stars, but for O-stars producing new mass loss rates. And what he found is that he found, that's Robin, by the way, who found mass loss rates that are not the 10% difference, but are 30% different than the old predictions, old models that we have. And this 30% difference is very significant if we look at stellar evolution. So 10% is a bit less, but it's like still same order of magnitude. So I definitely think that it's worth to dial more precisely than having a 10% error. Yeah.
Okay, and then a final question from Tom basically is also a technical question. At one point, you showed us this formula on how the line opacities basically get parameterized, but in there or behind getting that, you have this whole the Munich database that you actually handle and that you sort of treat with a Sobolev approximation, and then basically that ends up in some factor in there. Now, my colleague and myself are also quite exposed to solar physicists, where the Munich database doesn't say anything, but the Chianti database is something that people use all the time. Are you aware of clear differences, overlap, things that are similar or worth looking at in has to, because
So-
they really describe
yeah.
very
So
similar.
again, an new colleague actually now, he was a master student with us, Dapian, looked actually in his master thesis at comparing new databases or comparing multiple databases, basically to create one better, more complete database. And this was mainly the incompleteness or the difference was mainly at very high ionization stages. Yeah? So that means iron that's, I think, 8 times to 10 times ionized. If I remember. Important differences there, but this happens only at very, very hot temperatures. This doesn't really happen in, especially not for Wolf-Rayet stars, it doesn't happen in the wind, that happens deeper in the core. So I think for wind physics, we're quite well suited with our Munich database. This is also the database that's used in fast winds, which is the code that is like the standard for, or one of the standard for okay.
Okay, thank you very much. Then I guess I'll move on with my own questions before I give the floor to the promoters. Let me start by congratulating you as well. I mean, this is a fantastic work that, for me, for instance, it was indeed very satisfying to see that with your contribution, you now open up a whole new research field that will be possible with a code that I have quite some familiarity with. So thank you for that. The questions I'm gonna ask are then also a bit more on the, the horizon part of your work. At the very end, basically, you also made an effort to talk about how good can we handle anisotropic diffusion. You noted that you have this term that is basically treated now, in isotropic fashion, but at some point you may want to go to anisotropic diffusion treatments. And you were very optimistic, and you actually quantified that okay, the errors are small, but the anisotropies that you did allow in that test, it's on somewhere page 147 or so, it's anisotropies of a factor of 10, let's say. And coming again from solar physics, where we also have to deal with things like thermal conduction, which are essentially along the field, but then you have ratios of order 10 to the 12, not order 10. So how ready is your modification or improvement to the anisotropic diffusion treatment to go to much higher contrasts, or is it not ready?
No, not very. So the big limitation here is, I think, the diffusion solver that we use, right? So this is this multi-grid method that Janis developed. And yeah, no. So that's where the limit is. It's just the numerical solving. I think the theory of doing anisotropic diffusion itself is fine and doable to a certain extent, but the solver, the numerical solver, doesn't converge quickly enough.
Okay, I guess that's probably also going to be your answer to my next question then, because you cheated, right, when you showed your simulations as if it was on a spherical grid, but it's really right. This is cheating, right? You did it in a straight column, and as far as, let's say, the hydro dynamics is concerned, everything is ready to go to spherical. So is that the answer? Is that
again
that the only
the diffusion solver? But it's in general hard apparently to solve the diffusion equation in spherical coordinates. Multigrids, or the way that the Emarvec multigrid method is implemented doesn't work, because in your Laplacian operator, you have these prefactors that go as 1/r², and in your diffusion operator, in your multigrid solver, you want basically all terms to be more or less on the same order of magnitude to converge efficiently. That being said, I haven't tested it. The anisotropic solver that was a factor of, I think I went to 100 actually. That worked, or seemed to work, even though that it was also not thought to work. So maybe we should just try it. Maybe we should just try to. Another possibility is maybe to split the diffusion step in one lateral step and one radial step, and then complicate the IMEX scheme a bit to two implicit. I'm not sure how possible that is, but I think that's probably maybe a better way, to go about that. Yeah.
Right. And how far are we then from? So you showed us 3D simulations. One thing that struck me in your movie was that there's really a lot of variability. There were periods where there was a lot of clumps, and then there were periods with very few clumps. Is that also something that you quantified at some point? Also, the flickering. Is it right on the ballpark of observations, or can you make it more extreme or less extreme? Is that something?
So we've done some comparison of like indeed these photos. Let me maybe go back to the figure first. So Ronnie's talking about this figure here on the bottom, where we show the variation of light with respect to time, how the star flickers. And so to answer this, magnitude-wise, yes, there are stars that have a similar different magnitude than what we have, but time period-wise, we're a bit off. I think a factor of 10 in the periodicity or in the signal that we're a bit off as compared to the whole range of Wolf-Rayet star that has been observed. That is to say, the Wolf-Rayet star that we've modeled here is quite on the low end of mass and size. So we're not really in the center of where all observations are. So we don't really know that many stars, that many Wolf-Rayet stars with 1 solar radius and 10 solar masses. So an interesting follow-up would be to explore the parameter space a bit and see if we can actually translate these different stellar parameters to different periods or frequencies and magnitudes in the signal.
Okay, thank you very much, Nicolas. That was more than satisfying to me. So I'll give now the floor to maybe first Ilek to ask you some more questions.
Thank you, Ronnie. And thank you very much, Nico, for this excellent presentation of the work you carried over the last 5 years. So I will have a few questions, but I already had the time to ask you many for the last 4 years. Regarding first the last, so some parts which are in your manuscript, but weren't in your talk, because for the sake of the clock, you had, of course, to downplay some side projects you started at the end of your PhD. I'm thinking about winds from accretion disks, so an alternative but very exciting environment where your work would have a very, very fruitful consequences and would be really useful, and an environment where you can have a lot of UV photons to drive this line acceleration. So you've been asked by Ronnie, or rather by Tom through Ronnie, about magnetic fields. And I know that you also have these magnetocentrifugal disk winds, which are really famous and appreciated on the market. So if tomorrow you had to be the champion of UV disk winds, what kind of, where do you think they'd be the most suitable to compete against the magnetocentrifugal models? What kind of disk winds would be the more relevant for what you did?
So disk winds where the UV driving is more relevant than magnetic driving, basically. Whew. No idea, honestly. So I think in CV winds, typically magnetic fields, so cataclysmic cataclysmic variables. These are stars where you have basically a binary object where one of the two stars is a white dwarf, so this very compact, dead young star, and you have material from the secondary star that's being accreted on this white dwarf, forms a disk. This disk heats up due to gravitational things, and then you create a lot of UV photons that drive a wind from that, and this wind we can also see in absorption. So I think that their magnetic fields are probably not that important because these are low mass stars. No.
Depends on the type of white dwarf, but yeah, okay.
AGNs are, of course, like I think magnetic fields are very important in AGNs, but I'm not
Also,
an
but
AGN
like
person.
that could be an environment where UV are important also.
I
so,
think
yeah.
maybe for these disks, what I know about disks is that they try to explain different regions of the disks with different phenomena, right? So I think that the outer side of the disk they typically describe with also this pressure gradient, and if you get closer to the center of an AGN disk, this is more UV driving. But then in the middle, you need some X-ray shielding or something for which you need this magnetic fields to pop up dust. It's all very. I'm not an AGN person, but yeah, I think it's maybe dependent on where you're looking in the disk.
So, because you opened the dust Pandora box, now I have to ask you a subsequent question. You showed this transition diagram, great transition diagram, and with an incredibly frightening number of transition lines. I think you mentioned something like 40,000. So I'm not going to count every single of them. I trust you. But how do you explain that we manage through databases like the Munich database or the Canty database to reduce this very complex transitions into effective opacities, which are very simple, very straightforward? And how do you explain that it's much more difficult to do so when we are in cooler environments, so environments which were not really at the core of your PhD, but which are of interest for other members of the AVS?
Yeah. So I think one of the things that we do with our atomic lines, as opposed to dust or molecular lines, is we assume that these lines are very thin, and I think typically neglect the fact that these lines can overlap, which is probably good for atomic lines, but this is definitely not the case for molecular lines or for broad absorption from dust. So in molecular radiative transfer, you're very you have to really take into account how different lines overlaps, and also in molecules you have lots of lines, of course, right? So I think
Okay, thank you. And a final general question concerning your work on O subdwarfs, well, on Wolf-Rayet and O subdwarfs. So in computational astrophysics, it's pretty rare that you run into something in your simulation which is not a numerical artifact and that you were not looking for in the first place. So like a surprise physical mechanism. So your PhD was about getting stuff out of the star, not getting stuff falling back on the star. So when and how did you realize that this failed Wolf-Rayet wind simulations were relevant for O subdwarfs?
Yeah, so I think this is also something that's been expected before, right? That in different, so if we look at different metallicities, such as in the large or small Magellanic clouds as compared to the galaxy, we see that the population of Wolf-Rayet stars stops at a certain luminosity threshold, and this threshold changes with respect to metallicity. So it's different for the LMC, it's different for the SMC, and different for the galaxy. And so that sort of starts to beg the question that at some point these stars, they might be similar object, but they just don't produce these emission lines anymore, right? So then there has to be some sort of accompanying object, which is basically a Wolf-Rayet star, but without these emission lines, because you don't have this thick wind anymore. And so I think working from there, you can get to the fact that these are like O subdwarfs.
Okay, thank you, Nico.
Okay, so the discussion will be continued by your promoter, Professor Junquist.
Yeah, I've asked a lot of questions, Nico, during that. So I won't ask so much. But one thing I'm curious about, and it's going to be vague, like Dylan's. But one of this, I mean, you started a new, in my opinion, very interesting job already, actually, which is seems very exciting. And it's also about code development and stuff like that. So what do you think? Of course, it's different type of applications, right? So what from this, in general, do you think you can bring with you? What skills are, you think, the most important that you transfer, so to speak? And also perhaps a little bit, what have you had to complement with in yours so far, and what do you feel like you need to still complement a little bit with?
Good question. Very
Or are you already
deep
perfect?
question. I'm quite no. I've started in meteorology, where we also do a lot of hydrodynamic simulation, basically, of our atmosphere. But the reason with which we do this is completely different, right? So one of the biggest changes that I've noticed is in our meteorological models that we run, is we sort of try and slap as many parameters and knobs into our code, thousands and thousands of tunable parameters, to get the best weather predictions possible. And this is not the case in astrophysics, where we actually want to have as many free parameters as possible to sort of understand the physics. So that's like a completely different approach to basically solving atmospheres, right? The dynamics of atmospheres. So other than that, what I can definitely take with me is a bit of understanding of hydrodynamics, a bit of an understanding of how these codes work, how code development goes. So yeah, vague answer for a vague question. Yeah.
Yeah, I think that that puts it good to an end. Very big congratulations, as I've said many times. It's a benchmark thesis. It's as simple as that.
Thank you.
Okay, Nicola. Thanks, John. So this is a public defense. So also the audience has possibility, option to ask questions, but you should indicate that or do that now. Okay, can somebody pass the mic?
Right, thank you, Nico. It always amazes me to see these detailed 3D simulations. So that's really cool work. However, as you know, I'm like a 1D stellar evolution modeler. Do you have like tables ready where we can just take our photospheric parameters and pick a mass loss rate? That would be like extremely useful. You've shown now for like one mass and one radius of both Wolf-Rayet stars and O stars. But can you easily extrapolate these results to higher mass, lower mass, larger stars, smaller stars, etc.?
Yeah. So in theory, yes, definitely. Yeah, we can run our code for a wider range of variables. But I'm not so sure if that's actually the best way to get to mass loss rates. I think there are tools that are like power. I think those are still a bit better at producing actual mass loss rates. These computations are also maybe a bit too expensive to just run tables upon tables, while a power model can run on your laptop in probably an hour or something. So would be possible, but I'm pretty sure that's probably not the best.
So then you suggest to calibrate some power models to your thing and then scale via.
Yeah. So indeed, we can definitely compare 3D effects on or look at how our 3D models compare to power models for the same star.
Super.
And then,
Thank you.
Yeah.
Anybody else? Please don't hesitate. It's your last chance.
Apparently, there is also a YouTube live chat, which I cannot see, but I don't know whether there's a question in there. No? Okay. Then, if that's the case, then we will, close this part of the session and reconvene shortly.
Okay, ladies and gentlemen, dear colleagues, I now proclaim the results of the deliberation by the examination committee appointed for granting the doctoral degree in science physics. Nicolas Moens has presented to the faculty his PhD thesis on the topic Radiation Hydrodynamics of Massive Star Outflows, in partial fulfillment of the requirements for the PhD in science physics, and he has defended this thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer you upon Nicolas Moens the degree of Doctor in Science Physics, and I close the session. We close the session, but your promoters still want to say something, and I suggest that we go sit for that.
Yeah, okay, yeah, I'll start then. Okay. So, Dr. Moens, how are you feeling?
Less stressed than
That's good. That's how it's about. Less stressed than you've been in 6 years.
Het is nog niet gedaan. Nee. Nog niet.
Ja, denk
10 minuutjes.
Ja. 10 minuutjes.
Catering.
Twee
People are thirsty then.
No, it's been quite a journey, huh? It's been the thesis, of course, 4 years, a little bit more, but then also the master, not to be forgotten. And it's one of the things, of course, you have outlined very, very nicely the sort of say groundbreaking development work. And I say this also a testament that, you know, good modeling takes time, patience, and it's not always perhaps, yeah, sometimes there are struggles and stuff like that, but we came out, you came out very, very nicely in the end. I hope this is also something you can take out into your next challenges and the modeling there. And I actually looked yesterday at your master thesis, which has a very similar title, Radiation Hydrodynamics with MPI and Marbach, but there is no model in the image here, and that was, of course, because we weren't there yet. But now, very nice on the cover of your thesis, we have a model of a Wolf-Rayet star, and indeed, this is not an artist impression, which is almost always the case in our field. It's also not this nebula that you show, which is basically the nebula with the star as a point star. This is actually a real Wolf-Rayet star model. So it's quite an accomplishment. So congratulations to that. Now, and I said that it has been struggles, but actually when I thought back about it, there hasn't been so much of significant delays. It's been fairly, you know, going quite steadily, chaotic at times, as you wrote yourself in your thesis, but fairly straightforward. I thought about again if there has been some real hurdles, but it wouldn't be anything that go, you know, on the top range of the Cormack scale, I think, in terms of the scientific work. At least not that I can remember. Perhaps you have withhold something for me, but yeah, you stayed at least in the middle range on the lower part of it, I think. On that, that's of course scientifically. Socially, I'm not so sure. Might have been higher on the Cormack scale there, whether it's in terms of going skiing and you know losing your phone or whatever, or planning ski trips in the work email. That's also that one can do. Or for that matter, I've seen of my previous generation, some very suspicious calendars scattered around the institute. So I don't know. Those I play higher on the scale. Huh? So even if you might not be around anymore, certain parts of you are, so to speak. Anyway, it's of course been very nice days for me, and I see this also as it's indeed a little bit of the end coming of the first generation. It's very first generation, so to say, of graduating students culminating with you here today. It's also nice to see the other ones here in the audience, right? And actually, that's something that I personally appreciate a lot. It seems like you all still hang out quite a bit together, you know, whether it's being with badminton or volleyball or even going paragliding, or supposed to, I've heard. So that's very nice. Seems to be a social occasion for everything, even if it's during a winter school in Tenerife. I hear that there's more time in the festivals, but okay, that's good. There was a lot of science done in the end, so that's very nice. Now, these first generation, I would say, of 3D massive star atmospheric models, it's really a benchmark in the field. So they will certainly, your thesis here will live on for a very long time. It's indeed where the next generation of students in our group are basically taking off, I would say. And also another very nice thing with Nico is that I've only ever heard so positive comments about students and other colleagues who have worked with Nico. Everybody says it's so nice, so helpful and stuff like that. So that's something I really appreciate over the year. And I also hope it's something that you get to take into your There you go. Not all heroes wear capes. Of course, when you dig into a little bit more what Nico's going to do now, right? It's not the long term well-known. It's actually the short term. So essentially, it's going to be the weatherman. And I don't know if you thought that this would be less stressful or anything, but you do know that people tend to blame the weatherman on quite a lot of things. Why wasn't it sunny today, or you know, why didn't my beer taste good enough, or whatever? You can always blame the weatherman. So I got you this little stress ball, which is a globe, and it has no cities on it, which is essentially Nico's task to model the effect of cities. Right? So when you're too stressed, that could be a world without cities. Yeah? But I suspect that it's not going to be enough because, like I said, if there's something people like to complain about, it's the weather and the weatherman. So when everything fell, you can just look at this, or you can tell them this. So this would be the final tip there.
Zoiets het is als de weerman loog, dat is nog Als de weerman loog, bedenk dan tussen de druppels door, dat is het droog.
So, that will do. And everything, I'm sure everything will go great. And good luck with that. And your work here will certainly live on. It's already, like you mentioned, we're already doing all of that. So, congratulations, Nico.
Thank you.
You should be very proud.
And I'll add a
few words as a co-supervisor. We'll keep it short because I understood that the buffet is waiting for us. But dear Dr. Moens, dear colleague, so thank you for all this work and all these years. I want to stress on how ambitious the project you carried out was. I remember back in 2018, our discussion with John about the broad set of skills which would be required to make progress on the question. At that time, most, if not all, models of stellar winds of massive stars were 1D. And John has just started to venture into the realm of 2D. And now, when I'm looking at the cover of your manuscript, I realize how you went much beyond our craziest expectations at that time. So I think that's a fair representation of what you accomplished and what you can be proud of. I remember already during your master internship how you overcame the technical difficulties of bridging the gap between the physical models on one side and functional numerical simulations on the other side. You quickly handled all the numerical aspects and harnessed very complex and sophisticated code, to the point that I wonder whether you ever really needed your yellow rubber duck to talk to in order to debug and implement your model. Did you
Definitely, it's now my new office vehicle.
Okay, I'm happy to see that weather forecasters are in good hands now. It's like so. In addition to your scientific proficiency that John already insisted on, I mean, you brought to the team your cheerful and enthusiastic mood. I remember that you never shied away from sharp and relevant questions. And after all these years, I can definitely say that your insights have been of tremendous importance for my own understanding of the topic. So I will finish with a warm thank you well, which is the best I can do in Dutch until today, sorry. And for making this collaboration so stimulating and so intellectually exciting. I'm sure you'll be dearly missed at IVS in Leuven, so please visit Santiago if you pass by, which doesn't happen every day, I guess, but still, if you come by boat. And all the best for your new work at RMI.
Thank you so much. So, since Jan always to the computer. Since Jan always gives T-shirts at the end of PhD defenses, and he's a bit of a football fan, he has a thing for switching T-shirts. So I have two gifts for you guys.
Thank you so much.
Thank you so much.
Thank you so much. Should I open up?
Yes, please.
I'm curious. Supervise Nico, which is supervise.
This is great. This will definitely be worn.
Next time I supervise a Nico.
But possibilities are.
Thank you very much.
Welcome. For the rest, thank you to everybody for coming. It's amazing to see so many people turn up to learn about stars. This morning, or this evening actually, I was quite stressed during the night. And I kept Tess awake a bit, complaining about my stress. And then Tess said, it's fine. The people that are there, they're going to be there for you and they're going to help you. And that's really true. And then for that, thank you to Tess for soothing me and for all of you for being here. That being said, enough emotions. There's a reception going on. So let's go get a drink. Let's grab a bite.